Okay, let's consider the adiabatic expansion of methane behaving as a perfect gas. Oops, turn that off. 4.5 grams initially at 310 Kelvin, occupying a volume of 12.7 liters. Expands adiabatically, behaving as a perfect gas until the volume change is 3.3 liters. So I began this question, and I apologize, I began it before the thing started to record. So rather than start with a clean slate, we just have a bit more on the paper. So the black was what was given. We're asked to find QW, delta U, delta H, delta V, delta P, and delta T, which really exhausts all possible questions that we could find solutions to given this information. So the first pressure was not actually given, but because this methane is behaving as a perfect gas, then I know that I can write it as nRT1 over V1. It is a closed system. That's always our assumption unless told otherwise. And so N2 is equal to N1. I'm given the mass, and I know the identity as methane, so I can determine the number of moles like this, the molar mass. I wanted to go over these and ask you to think about them, but anyway, they're now displayed. So T2 is less than T1. I'm not given any of temperature, temperature, volume, or pressure in this second and final state. And I wanted you to think about whether or not the temperature in the second state would be less than, equal to, or greater than the initial, and the same for volume and pressure. Because the gas is expanding, then work is leaving the system and going to the surroundings. Work is being done on the surroundings. So energy is leaving the system as work. Because it's adiabatic, that restriction tells us that there is no Q coming into or out of the system. So if work is leaving and there's no Q entering, then the net effect, of course, is that there has to be a drop in internal energy, and this is demonstrated in a drop in temperature. The gas cools when it expands adiabatically. Of course, if it's expanding, the final volume is greater. And we also have a pressure drop in an adiabatic expansion because you're going to a larger volume and with the same amount of moles, but the temperature is dropping. And so you have a pressure drop as well. So now, qualitatively, that's great, but we want to find some, in fact, all of the numerical answers here for these. So as I said, I had started before I realized the camera was not on. So the obvious place to start, I think, and we've done this really as a rule of thumb in these questions, is to look at the restriction. Sometimes it's isothermal, sometimes it's constant volume or isochoric, sometimes it's a constant pressure or isobaric, and this one is adiabatic, which means Q is 0, and so that's where I've started, and that's why the first question there is circled. And what do you think about next? Well, you're probably trying to think of formulas to remember to find T final or V final, or that PV gamma is a constant and how they'll be used here. But just take your time and let's think about this logically. After all, this is what we're supposed to be getting out of all of these mental exercises. So I look at the restriction. What does that mean? Oh yeah, it means Q is 0. So what flows from Q0? What's Q related to? And that's first law. So let's let one fact lead into another statement. du is equal to dq plus dw. That's always true, regardless of what kind of path you've got. But dq is 0, and so du is equal to dw. So that's what's written here. And underline the subscript AD for adiabatic, because people still wonder, how can you equate a state property with one that depends on the path? Well, the path is not varying anymore if I actually state it. So when there's an adiabatic connection between the initial and final states, my work is equal to the change in internal energy. And so that would integrate as delta U is equal to adiabatic work. And I know that du, which is what I've done here, du independently is equal to NCV molar dt. So delta U would integrate as NCV molar delta T, if I can safely assume, and I would, unless otherwise told, that the heat capacity is independent of this small temperature change and staying constant. And so that sounds like a good ticket forward. Oh, I'll just use this. Delta U is NCV delta T. And I know N, and I know CV for a perfect gas, or I could look it up for methane. Depends on how I'm instructed. And then I would write in delta T, except I only know T1, I don't know T2. And so I kind of halt right there and think I need to find out what T2 is. And so that's when we come back to this statement, and this becomes a starting point for that derivation that we're responsible for. Now, if you remember the formula for T final, then you can jump right into that and get on with it. But if not, then let's just do this. Okay, so du is N CV dt. dw is always a minus P dV. Let's leave this the way it is for a moment. And I'm going to get rid of the pressure, and I want to express it using PBNRT because this is a perfect gas. I want to express it in terms of the other parameters, nRT over volume. But I really want to pronounce the relationship to the dV. And so I see that, I'm getting ready for my integration, which is ultimately going to follow. Now I see that there are two things changing, temperature and volume, so it's good to have them each on their own side of the equal sign. But likewise, everything to do with volume is on the dV side, and everything to do with temperature should be on the dt side. And before I do that, I just want to recognize that I can simplify this a bit and cancel the ends. So now I'm going to bring temperature over to here, but I'm going to write the constant first and then write it as 1 over T dt. And so each step makes a lot of sense. I'm going to put a circle around the negative sign because it tends to get lost. Our temperature went over there, so I'm not going to repeat it. See, when you do this thing rather quickly, and you know it, that's when you make a mistake. Force yourself to think about each step and make sure that it makes sense. The next thing we do in formula developments is to bring together what are constant to one side or the other of the equation. Now, if I bring R over here, I'll be left with CV over R. The negative sign can stay behind, and I'll take care of that later. But I can think forward in my head for a moment that won't leave a nice uncluttered ratio of T final over T initial. And I'm after a formula that isolates T final equals. And so what I'm going to do is take this constant and bring it to this side. And that will leave, quite simply, what will become a temperature ratio solution uncluttered. I have a negative sign. This is R over CV multiplied by 1 over V dV. Okay? Now what? Well, now I want to integrate. And just for the purpose of this, I'm going to write this out with integral signs instead of skipping that step and just saying, now let's integrate, and we'll do it in our head. So integral 1 over T dt, nice, easy integral solution to solve. What is constant stays in front of my integral sign, right? And now I will solve this between the limits of T final and T initial, or T2 and T1 respectively, and that solves as the ln of T final over T initial. So I'm using more generic terms of final and initial, but I do know that I initially set up the problem as state 1 and state 2. and then I have R over CV, carrying that negative sign always, the ln of V final over V initial. Now I want to get rid of these lns, so I want to take the inverse ln of both sides, and that will leave me with T final over T initial equals. Now how about that negative sign? Before I take the inverse ln of this side, I want to actually, perhaps we can combine it in a single step. This negative sign, if I flip this ratio, that would take care of the negative sign. And so this will be, the next inserted step in here would be a plus R over CV ln V initial over V final. And so the inverse ln of that is going to be V initial over V final. What happens to your operator here on the ln is that it pops up and becomes the exponent. Now for the purpose of plugging into this formula, as we say, T final is equal to a fraction of T initial, and that fraction is V initial over V final, and then I have R over CV. Now just a moment here, this R over CV. This is R over CV molar. And if I knew the CV, let's back up a second. If I knew the heat capacity of methane, it would most likely be given to me as a CP value in joule per K mole. And I'm just going to look at the data sheet that I did generate earlier. There it is. And yeah, I've got a value for that in precisely those units, joule per K mole. Now, I just want to mention here that if I didn't have a specific value for methane, then I would use the general value for a perfect gas, and that is, and I know that we said the gas is behaving perfectly, but what that allows us to do is to make use of the relationship PV/nRT. It doesn't necessarily give us license to use 3/2 R for CV. If we know the identity of the gas, we should probably be using the real heat capacity. Okay, so I'm just going to put an asterisk there because you really just want to hold on and see what you're allowed to use. Of course, if we were using 3/2 R, the R's would cancel and I would be left with an exponent of then 2/3. So that's really easy. But let's leave this as R over CV molar and just refer to our data sheet that for methane gas, we know that CP molar is given as 35.31 joule per K mole, and therefore CV molar is equal to CP minus R. So I'll just grab the calculator and take a value of R away from that. So 35.31 minus 8.3145. And that leaves me a value of 26. Well, it's 0.99. I'll leave it like that. It's two decimal places carrying. Joule per K mole. So that's the one that I'm going to use here. Okay? Let's get some more room. So back to calculating T final. It's equal to, T initial was 310 Kelvin, and that's all multiplied. V initial is 12.7 liters. Doesn't matter what the units are because they're going to cancel and the ratio is the same. V final is 12.7 and 3.3, so 16.0. And up in the exponent, I have 8.3145. Don't put the units yet. Divided by 26.99. What are the units of R? Joule per k-mole. What are the units of this guy? Joule per k-mole. So they're going to cancel. Okay, so just like I can't take the natural log of a number with a unit, I can't have units in the exponent either. So if you throw in numbers into an exponent and don't cancel all the units, there's something wrong for you to go check. T final then is equal to, all right, let's actually calculate what the exponent is. 8.3145 divided by 26.99. So just because this is a tutorial, I'm really dragging out the steps so it's clear for everybody. Because of course you don't have a chance to say, hey, where'd you get that? Chance to ask a question? Well, I mean, yeah, you know what I mean. Y'all can email me if you want. And then that's 0.30858. Yeah, I'm just using the number in the calculator because I'm not actually deleting it and carrying that all forward. So 12.7 now divided by 16 equals, and then that's the volume ratio. Make sure you know how to raise a number to an exponent using the calculator that you're going to use in a test situation. So you're not trying to figure that out during a test when you're alone. And yeah, having said that, yeah, so that's my x to the y. X to the y. 0.308058. Okay, so I see that my temperature, my new temperature is going to be just 93% of the initial. So 0.9313 times 310. There we go. So I am expecting a temperature drop. That's great. It's going in the right direction. Seems right. 288.7077, etc. units Kelvin. I should have 2 sig figs. So T final is 290. Great. So therefore, delta T is equal to T final minus T initial. So let's use the 2 sig fig one. 290 minus 310. I don't know why I'm using a calculator. Minus 20. That's what it is. Minus 20 Kelvin. Okay, that's my delta T. Let's go back up here for a second. What have we got so far? That was 0. We just did delta T. So now we can do these guys work and delta U because it's going to integrate here as NCV molar delta T. So let's do that. Delta U is equal to the adiabatic work is equal to N CV molar delta T, and that is equal to my N you may have calculated N separately, that's great. CV molar, which I just used above, it's CP minus R. And delta T. Don't forget that negative, it's a temperature drop. Units. End up in joules, that's great. 20 is still there, so we'll carry it. Multiply by 26.59 times 4.5, divide by 16.043. The internal energy is decreasing. There is a temperature drop. There is work leaving. So all the sign all makes sense everywhere. And we'll write this as 150 joules. And that is for both delta U and work. Now delta H. Delta H is what? Now we start. H is equal to U plus PV. Therefore, delta H is equal to a delta U plus the delta of the PV. And we'll write that as delta of the nRT. And that means I've got N2RT2 minus N1RT1. N and R are constant, so it's really NR delta T, and as I said, very important in the adiabatic change. So delta H is equal to delta U we just found. It was the same as the work, and that's 150 joules. Plus, here we go with that N again. I'm just going to calculate it. 4.5 divided by 16.043. With 3 sig figs is 0.280 moles. The R value I'm going to use here, which one should it be? Yeah. 8.3145 joule per K mole. And then the delta T, which we just found up there, I've pointed off screen, but it was a minus 20 Kelvin. So, units, Kelvin, mole, left with joules, adding to joules, apples to apples, lovely. And so, inside the bracket, I have this many moles times 8.3145 times 20 minus. So inside the brackets, it's a negative 46.64. And okay. So we'll be careful with everything. That's a minus 150 plus a minus 47, and it's all joules. So I did a 2 sig fig there. No decimal places, so let's just add these together. It's a negative and a negative, so 150 and 47 is 197. Okay. And that's delta H. Good. And that makes sense too, right? Because you expect delta H to drop. You would expect that change to be a minus. Yeah. Volume, easy peasy. Given. 3.3 liter. And delta P. Delta P. Right. Oh, I've run out of room. Need some more paper. What is delta P? adiabatic. What do we know about P, adiabatic? We know that PV gamma is a constant for an adiabatic change, right? Sorry. Just like PV is a constant for isothermal changes, PV gamma. Remember what gamma is? Gamma is Cp over Cv. And while we're at it, why don't we just figure out what that is? It's an easy ratio. It works out to 1.67 for ideal gases, but I'm going to use the real value here. So that was 35.31. I'm not going to put the units here yet. And Cv is that guy minus R, which was 26.99. Yeah, I know they have the same units. Joule per kmol, joule per kmol, zip zip. So let's find what is gamma. In some questions they'll actually tell you use whatever, they'll give you the value for gamma, but they didn't hear we were given a CP, so this is what we would do. 35.31 divided by 26.99, and I have 1.308. No units, of course. So that's the gamma that I'm going to use. Great. So what that means, if it's equal to a constant, then that means that P1 V1 gamma, remember it's not the product raised to the gamma, it's just V to the gamma, is equal to P2 V2 gamma. Let's isolate for P2. Then this guy is going to go under here. So that's P1 times, let's put V2 underneath V1. You see how that worked? Is that okay? Make sure the algebra makes sense for you. Let me just do it here. That's the step I skipped. Basically, I took this and I grabbed V2 gamma and that left P2. And then, because these guys are raised to the same exponent, I took their ratio. Okay? Keep that by itself. Okay, so P2 is equal to P1. We don't even know what P1 is. We don't. It's equal to nRT1 over V1. And then I've got V1, which I do know, 12.7. V2, which I do know, because I add 3.3, which is 16.0. And that's raised to the power of 1.308 because we just found out what gamma is. So P2 is equal to number of moles. We just did that. What did we get? 0.280 moles times R. Think about what value for R you want. Yeah, you want the one with the liter. 0.08206 liter atmosphere per mole Kelvin. And then temperature is 310 initially, so that's T1. And that's all multiplied by the 12.7 over the 16.0 raised to the power of 1.308. Mole, Kelvin, Kelvin. What did we forget? What did I forget? V1. So V1 has to go under here. And RT all over V1, 12.7 liters. So now that goes up with that. Perfect. I'm left with atmosphere. P2 equals. I did not do that on purpose to show you how important units are. But yeah, when you have these really compound solution lines with lots of different levels, it's easy for me, at least, obviously, to miss the denominator on one. Okay, I think what I want to do is this first, and then multiply from right to left, maybe. Get shadows of wires. What is that? 12.7 divided by 16.0 raised to the 1.308. So that's 0.739. Now I'm going to keep multiplying, so by 310, and then times 0.08206, and then divide by 0.28 number of moles, and then divide all that by 12.7. 0.4146 atmosphere. I just want to do that again. I'm hearing myself say, I'm not sure if I said that right. 12.7 divided by 16 equals, raised to the 1.308 equals, times 310, times 0.08206, times 0.28 equals, and then divide by 12.7, yep, 0.4146. And let's reduce that down to two significant figures, so 0.41 ATM, that is my P2. Sometimes we're asked for what the T2, P2 is. In that case, that's great, but we want delta P, and that's equal to P2 minus P1. So we threw P1 in there. Do you see it right here? Maybe we could just calculate that right now, or P1, because we did find P2. And so that's 0.28 times 0.08206 times 310 divided by 12.7. P2, 0.41. P1, 0.56. That's all atmospheres. And so delta P is equal to, oh, I don't even know why I'm using the calculator. There was a pressure drop, so we did expect it to be negative. That's great. 0.15. Okay. I think we're actually done. Well, pulling that ahead, but it was right here. Yeah, that was our last thing to do. So that's great. And you might be wondering again, what about this? Do you have to do that? You don't. You can just go right to here. If you've remembered it, they're so close. The formula for T final or V final. See, delta V was given here in this question, right? Delta V was actually given. But remember, there's one formula that we're not using here, and that's V final, which is equal to V initial times the temperature ratio to the CV over R. So they're so close, and that's why I've asked you to be your own source of information here. And so I've actually said you are responsible. Okay, if you are asked to, starting at the first law statement, show what the formula for T final is, or show what the formula for V final is, you have to be able to do that. But if you just asked, like in this question, not specifically for the derivation, but for the values themselves, and you're confident in your knowledge of the formula, then by all means go right ahead. But it didn't take very long for us to do that, and it's a sure thing then that you know what you're doing. Great.